I thank everyone for joining us in this afternoon to talk about research. No, so for those who are joining us from other universities, we're the Center for Computational Imaging and Visual Innovations. Our research focus on computer vision projects. So this is a research lab under ADRIC, which is under the College of Computer Studies in De La Salle University. So we acknowledge there are some participants joining the lecture for today from the University of the Philippines, from Adamson University, from FEU, De La Salle Lipa, Northwestern University, and Manila Central University. So thank you for joining us. And for the rest of the DLSU students and also research students who are under our research lab. So we organize this academic lecture so that we get to learn more and prepare our students for the computer vision research that they're going to do for their thesis. So most of our participants are our undergraduate level students who will soon do their thesis under our research lab. So that's the background of our academic lecture. So we are going to explore 3 different topics this afternoon. Actually, we are only going to have 2 lectures for today due to some scheduling conflict. I will introduce the speakers that we have for this afternoon. Both are from our BSMSCS honors program. So the first topic or the first talk that we're going to have is transfer learning for medical image classification. Let me read through to you the abstract of the presentation. The development of deep learning models has greatly contributed to the advancement in medical image analysis. However, training these models from scratch remains a significant challenge in certain applications due to the lack of large labeled datasets within the domain. To circumvent the high cost of collecting, labeling, and storing large amounts of medical images, we know that transfer learning is one of the techniques that we can employ. It is the process of reusing learned information from a source task and applying it to a target task. This allows for reduced training time and competitive performance when data is limited. So in this lecture, we're going to understand or to talk about introduction to medical data, medical image analysis, some core concept in understanding transfer learning, challenges and limitations, and also real-world applications on where we can use transfer learning for medical image classification. So about the speaker for this talk is Christian Tia. He is an undergraduate student in the BSMS Computer Science program at De La Salle University. This is our honors program for computer science student. His research focuses on automated diabetic retinopathy classification and how it can be optimized in low resource settings using smartphone-based imaging. So I will now give the floor to Christian, who will present his lecture for this afternoon.
All right, so hello, my name is Christian Tia once again, and I will be discussing transfer learning for medical image classification. And so just to outline again what we're going to go through. First, we'll look at medical image analysis, what it is and what are the challenges that it currently faces. And then we'll look at a just a brief refresher on convolutional neural networks as well, and try to understand what each layer does in relation to the architecture. And then we'll talk about transfer learning, how it's implemented, an example of its application in real world use, and also some of its limitations. Okay, so first let's look at medical image analysis. So medical imaging is the use of technology to view or visualize parts of the human body for diagnosing, monitoring, and treating medical conditions. And so there are a multitude of imaging modalities that doctors can use to try and diagnose patients. So you have your CT scans, MRI, PET, ultrasound, fundoscopy, among many, many others. And so these images are captured in the first step of the typical diagnostic workflow, where the images are used by doctors to interpret, to gather a conclusion depending on a patient's medical condition. And then from their conclusion, a decision will be made about how to proceed with patient care. And so obviously this workflow is a very critical aspect of a patient's healthcare, and it can decide very like whether the patient can recover, or whether you detect the disease that they suspect to have, and so you'll be able to treat it. Otherwise, if you miss the diagnosis, then obviously that can lead to severe consequences for the patient. However, despite how critical this entire process is, there is still here, and of course, with anything human comes with human limitations as well. So currently, the challenges of human analysis, well, first, there are wide variances among interpreters. So this is true for both different interpreters. So let's say you have two doctors looking at the same image. So even though they're looking at the same image, they may come up with different conclusions depending on their training or background. So that's called inter-operator variance. Meanwhile, the same operator or the same interpreter can look at the same image at different points of their career and come up with different conclusions. So that's intra-operator variance. So obviously this is not ideal because you'd expect these images to have a specific like ground truth value. So having variances is not ideal because it's not as reproducible. Next, there is a trend for images to be growing in complexity and volume as well. And so it threatens to overwhelm the visual system of doctors, even those who have been trained. Because of course, well, first, there is a physical limit to how many images they can interpret in a single day without succumbing to fatigue. And so this leads to long turnaround times for patients to get their diagnosis, which is not ideal in critical scenarios where they need it as fast as possible. And also, there is a potential for missed findings due to high workload. And once again, not ideal. So now, a lot of you may have already guessed where this is going. This is where AI and deep learning specifically can step in and support the medical system. Thankfully, diagnostic tasks require visual pattern recognition and highly structured images. And this makes them particularly suited for deep learning applications. So for example, here we have a fundus image, which captures the appearance of the retina at the back of the eye. So already we can see that these images are highly structured because they come in the form of these circular images. They capture the same thing, which is the retina. And so doctors use these images to try and determine whether a patient has a specific eye condition, for example, diabetic retinopathy. And they do that by recognizing patterns within the image that can indicate the presence of lesions, which from their experience, they'll then determine whether or not the patient has that condition. And just like how doctors can be trained to visually interpret or visually distinguish these patterns, so too can deep learning models, so long as there is sufficient data for the models information from. And so when done correctly, it will bring benefits such as faster diagnosis. Obviously, a model can be able to calculate a lot of these things very quickly. It also provides high accuracy and a very scalable solution. So this goes hand in hand with the faster diagnosis. So imagine how many images a single process within a single day compared to a human. It's probably orders of magnitude more. And the benefit is that they don't fatigue. So yeah, it will be a very valuable tool for medical experts if these models can be developed suitably for their applications. However, there's a very big caveat that I mentioned, is that deep learning models require large data volumes to be able to extract knowledge. If you're familiar with ImageNet, ImageNet, it was such a revolutionary data set in the field of computer vision because it contained such a large volume of data, I believe over with 1,000 classes. And so they were able to extract all of this, or they were able to gather all this information because the images depict everyday objects. And so they're able to crowdsource the labeling effort from lots of people. Multiple people can help with annotating because the general public is able to distinguish a cat from a dog, and etc. Unfortunately, such is not the case for medical images. Obviously, they require one or more medical experts. So me personally, I would not be able to tell the differences between these images, whether it has viral pneumonia, whether it's normal or has COVID-19. To me, they look, they all just look like x-rays. And that's because I haven't been trained to recognize those patterns. You have this limitation now for labeling where you need trained experts, and that inhibits your ability label large volumes of data. And furthermore, there's concerns with patient privacy. So these scans may have confidential information baked into the image. For example, the patient's name could be written down somewhere in the pixels, or the age, etc. And so special care must be taken for the people making the data set to ensure that they're protecting the patient's privacy and they're complying with all data regulations as well. And this entire process leads to this being very expensive, very labor intensive, severely limiting the ability of researchers to acquire or curate these medical imaging data sets. So this is where transfer learning step in. So in scenarios where data is scarce, you'd need to leverage knowledge from somewhere else. And that's the key thing with transfer learning. So how it works is that you have a classifier which learns or pre-trains on task A. And then once you've acquired that knowledge from task A, that's your source task, you'll start with that knowledge and further train the classifier on task B, your target task. And obviously your goal now is for better performance on task B. You no longer care about how well you perform on the source task. And this is done in the process called fine-tuning. So this is analogous to when you compare two people. Let's say, here, I'll annotate na yan. Let's say you have two people. First person does not know, this first person does know how to ride a bike. They've learned from a young age how to ride a bicycle. So obviously they know, they've hardwired their brain to steer a two-wheeled vehicle. They know how to balance on a two-wheeled vehicle. Even though it's a pedal bike, which is different from a motorcycle, this is still valuable knowledge. Now, the second person does not know how to ride a bike. So they're starting from scratch. And everything that they learn regarding two wheels has to come from motorcycles. Okay, which one is going to learn how to ride a motorcycle faster? Obviously, it's the first person who has knowledge on riding a bike. Theoretically, they need less data points on a motorcycle to be able to say that they know how to ride it because they have all this prior knowledge that they can leverage for the motorcycle. All they have to do now is just fine-tune on how to, use the throttle or get used to the power of the motorcycle. But in the end, it's much faster. It requires less training. The second person has to start from scratch, so it's going to be much longer. And if they have less time overall, they may not be able to sufficiently master the act of riding a motorcycle. So that's the very concept of transfer learning at a high level. Okay, so next slide. All right, so I mentioned here starting with the knowledge from task A. So now this begs the question, where is this knowledge stored? Well, to answer that, we can look at the most commonly used architecture for image classification tasks, which is the convolutional neural network. So we have two sections here, the feature extraction and also the classification section. And we'll look at to try to see what knowledge is stored in each one. So first you have the convolution layer. This is the most notable layer, of course, because this is where the architecture gets its name. Here, filters or kernels are applied on the input image in a process called convolution. So these filters, initially they start from random values, and then through backpropagation, they're trained to extract relevant features from the input image, which the network deems relevant for or useful for determining what the image depicts. So here's an example, very basic. You have a 3x3 kernel here. The size you can set yourself. And so let's say it's been randomly initialized to 1, 2, 3, 4, 5, 6, 7, 8, 9. So you take an equivalently sized image patch from your input image. In this case, it's just been simplified to ones and zeros. But you take an equivalent size image patch, and you just do a dot product on these two matrices. So that's just element-wise multiplication, and then you just get the sum of all products. So if we just briefly do that right here, we have 1 times 1, that's 1, plus 2 times 0, that's 0, obviously, plus 3 times 1, 3, plus 4, 0, 0, 5 times 1, 5, 6 times 1, 6, plus 7, plus 0, plus 9. And if you add these all up, that would be 4, 9, 15, 22, and then 31. That's how you get your output value. And you just repeat this process depending on your step size. So let's say your step size is 1, you just shift your kernel and you select, you shift your image patch to the right by your step size, in this case 1, and you just repeat the process using the kernel, and you'll get your output, okay? And so the value of these kernels is that, let's say you have, the kernel was trained to have these values, let's say -1, -1, -1, -1, and you have 2, 2, 2. Let's say this is how the filter ended up after training. So just from visual inspection, we can tell that this filter extracts vertical lines from the image. So now, let's say our input image is the following. We have 0, 0, 0, 1, 1, 1, 0, 0, 0. So these zeros won't be counted since, they're zeros. Now our total output would be 2 times 1 plus 2 times 1 plus 2 times 1 equals to 6. So it put high value towards vertical lines compared to, let's say, if it was a horizontal line, 0, 0, 0, 1, 1, 1, 0, 0, 0, this would just result in zeros at the top, zeros at the bottom, and then you have -1, -1, 2 plus -1, which is equal to 0. So it extracted nothing from horizontal lines, but it emphasized that of vertical lines. And so in this case, the feature that it selected was vertical lines. And at the very shallow levels, it will only be able to detect these basic features like edges, like I mentioned, or gradients. However, as you stack these layers on top of each other, it will be able to understand more complex features. So from simple edges, now you move on to you see basic shapes like circles. And if you keep going, you'll be able to get high-level features such as complex patterns and very interesting shapes that the network deemed relevant for interpreting the image. Okay, but after each convolution layer, you have to go through, not after each convolution layer, but you introduce these pooling layers to have translational invariance and also to reduce the spatial size of your data, leading to less parameters that you have to calculate in your network. So, for example, if we define our pooling layer to have to be 2 by 2 with stride 2, you just take a 2 by 2 patch, and then you just get, in max pooling, you get the maximum value. In this case, it's 5. And then you repeat the process depending on your stride, your step size. Here it's 2, so we move on 2 steps to the right, and we get the maximum value once again, and you'll get your output here, which is just a summary, I guess. It's a downsampled version of your input to the pooling layer. And so now imagine if this 5 was in this pixel versus if it was here, the output would be the same. And so there's some degree of invariance here to translations. So let's say it places less importance on where exactly a specific feature is. It can move around, translate up or down to some degree without affecting the feature extraction as much. So that's very important to be able to generalize better on input images. And also you have less parameters to work with, leading to faster computations, and yeah, more efficient use of the model. And then once you're done with your feature extraction, you have your classification layer, which is a fully connected layer. It's the presence of certain features to calculate the probability of an image belonging to a particular class. So after your feature extraction, and also I forgot to mention, there are activation functions implemented in here to introduce nonlinearity so that you can capture more complex behaviors. But once you're done with feature extraction, you flatten your output, your feature map, and you input them into a neural network, weights and biases, which calculate the probability of an image belonging to a particular class. That's your fully connected layer. Okay, so now let's take a look at a very popular architecture for CNNs known as the VGG16. It's very straightforward. You just have a series of layers here, or blocks of convolution layers, your activation function, in this case it's ReLU, and then your max pooling layers. And so here you have 1, 2, 3, 4, I think 5 blocks of these layers before you reach your fully connected layer with activation function as well. And since VGG16 is traditionally or most famously useful for ImageNet, it has at the end here output layer of 1 by 1 by 1000 to classify 1000 classes. Okay, so like I said, you can train VGG16 on a very large data set such as ImageNet. And so we'll take a look at how that may look within the network and like which knowledge is stored where for everyday objects. So at the base layers, at the very shallow layers, you can only detect very simple features like I mentioned earlier, such as edges. So here in this cat, it will only extract these very basic lines. It doesn't know what an ear is, it doesn't know what anything else is. It's just extracting lines here at the very start because you just started your feature extraction. But as you go deeper down, you start combining these features. So from edges now, it'll be able to tell, okay, these two edges at this angle, that may be an ear. Okay, so now small parts of the image are being extracted. So now we have ear, we have small parts of the face being detected, and then eventually these are combined even further to larger parts. So now you have head of the cat, and you can have paw, you can have second paw. And so now that you have all these features, these very high-level features, your network will be able to use those as input to the decision process. Okay, let's say it has a head, it has 2 paws. Okay, most likely this is an animal such as a cat. That's the beauty of these CNNs. There, cat. Through the fully connected layer, it decided that this will be a cat. So now we can go back to the question. Well, where is the knowledge stored within the network? Well, the answer is the knowledge is stored within the weights of the network. So we saw earlier that base layers, shallow layers, extract very basic information. They contain basic information about the features. Meanwhile, deeper layers store more complex information. This also goes, holds true for the fully connected layers. So the earlier layers are more basic decision logic. As you go deeper down, it's more high level and then domain specific. So now that we know how the knowledge is structured throughout your convolutional neural network, we'll be able to determine which knowledge should be transferred towards the target task. Okay, and this is very important decision when fine-tuning. So let's quickly define fine-tuning. So fine-tuning is when, like I mentioned, you start with your pre-trained model. So you have a model, let's say it's VGG16. This has already been pre-trained, so this stores all the weights for ImageNet classification. And so starting with those weights, you start retraining on your target data set by updating those weights. And so when we say freeze now, what we do is we lock those specific layers. We can freeze layers and lock those values so that directly the knowledge is being directly used for your new task now, since those weights that have been extracted, such as like basic features like edges, can be useful towards our target task if if it's similar to some degree. And the similarity between the source and target task will be a very important factor in determining up to which layer should be freeze. So typically the safest would be to, well, there's different processes and strategies, when we'll look into that soon after. But so yeah, that's the first factor, similarity between source and target task. The lower your similarity is, the you only freeze only the earlier layers. And this makes intuitive sense because if your two domains are very different, let's say you have your first domain, poisonous versus non-poisonous plants, right? And then your target task at the end would be brain tumor classification. So these two domains are quite different. So at most, you'd only want to transfer the earlier layers because these contain very, very basic decisions, basic feature extraction, such as those edges and shapes. However, as you go deeper down, it may be irrelevant to our new domain. So this could be like more leaf shape, etc. So that's completely irrelevant to our new domain. So we'd want to be able to update these deeper layers to be more applicable to our new task, while keeping some relevant information from the earlier layers. Okay, so that's one factor, similarity between source and target task. Meanwhile, you also have your size of target dataset. So the smaller your dataset, the more you need to leverage prior knowledge for good performance. So if you have a smaller dataset, you'd freeze deeper down. Let's say like to here. This is just an arbitrary line, but you freeze deeper down because your new dataset has quite limited information. So in order to perform well, you'd need more information from a different task, so long as the similarity between source and target task is quite similar. So there is a quantitative way of determining the depth of knowledge transfer. This is known as incremental defrosting. Wonderful graphic here to try to determine what incremental defrosting is. Well, you start from your deepest layer. You start by unfreezing your deepest layer. So in this case, this is very high level information stored here. And so this is almost very similar to just using the pre-trained classifier on your target task. And obviously, performance in that case would not be good, especially if your two domains are not super similar. So in this case, we're starting with ImageNet and we're ending in retinal image classification. If we just use ImageNet and you freeze all those layers, we get a bunch of useless information that we can't use towards our target domain. And so our performance here, our accuracy, is very poor if our transfer depth is very deep. So incrementally, we can reduce the transfer depth. So we start unfreezing more and more layers, and we just record how well the model performed depending on this level of transfer, or depending on this level of knowledge transfer. So at some point, you'll reach a peak, the most optimal amount of knowledge transfer here. In this case, it's around 19. And then from there, it's going to go downhill because you lose all that valuable information from your source domain. And so this is a good way of determining. This is a hyperparameter that you have to tune, the depth of knowledge transfer, and this is one way of visualizing and determining quantitatively which layer to freeze up to. Okay, so now we can look at an example of transfer learning used in the real world. So brain tumor classification. This is a paper entitled Brain Tumor Classification for MR Images. So I believe that's magnetic resonance or MRI images of the brain using transfer learning and fine-tuning. So this is just their graphical abstract. So their task is to classify brain tumors from MRI scans. This is a multi-classification task. I believe they have 3 different types of tumors. I don't recall exactly which, the medical terms for each one, but they have 3 tumors and then also a no tumor class. So I think it's 3 classes actually for this task. However, the problem that they encounter, the MRI dataset that they found for this task is quite small. It only contains 3,000 images. And so if they were to train a model simply from these images, it may not perform as well as you'd hope, especially considering the importance or the criticality of this task, which is classifying brain tumors. So their solution is to employ a pre-trained network, VGG19, which was pre-trained on ImageNet, and utilize transfer learning to try to gain leverage some useful information for MRI images or MRI scans. Okay, so earlier I mentioned the use of layer-wise incremental unfreezing. However, they also propose the use of block-wise unfreezing, starting from the deepest block. So we have they define their architecture here. And then they define the blocks as a series of, they define blocks as being separated by these pooling layers. Here, so you have block 1, and once you start downsampling, you start your next block, block 2, and you go on and on and on until you reach your final block, which in this case is they define the entire fully connected layer to be a single block. Okay, and then they repeatedly fine-tune each configuration starting from the deepest layer. So we see here that when they fine-tune just block 6, they receive an accuracy of 86.81%, which could be better. So as they start unfreezing, 5 to 6, 4 to 6, the accuracy starts increasing. So until they realize deep fine-tuning was required because likely because the source task, which in this case like ImageNet, so is quite different from the target task, which is MRI scans. However, if you fine-tune all the way up to the first block, that doesn't mean that you're not transferring knowledge, because the mere fact that you're starting from these pre-trained weights, the direction of your model training. And so you can say that knowledge was still transferred, but it's just that the difference in modalities was quite large, so that they had to fine-tune all the way up to the earlier layers, and achieving an accuracy of 94.82%. And so when they compared their classification model with transfer learning, they found that it yielded the best performance compared to other models proposed by other researchers on the same data set. In this case, we have other models achieving 91.28%, 90.26%, and 84%, while theirs is the best one with 94.82%. And so this just shows the value that transfer learning can bring on small data sets. Like I mentioned earlier, if you have very few information you can extract from your target, you can utilize large amounts of data using a pre-trained network. Okay. However, an important consideration with all of this is that there is such a thing as negative transfer, and this occurs when the source domain is completely incompatible with your target domain, resulting in worse performance on the target domain. So if we look at this graphic here, we can see that if we train a model simply just with our target, we don't have a source domain. We train our model, we test our model on squares, for example, we achieve an accuracy of 70%. However, in this next scenario, we first train the model on triangles, and then we eventually fine-tune on squares. It actually yielded worse performance, and that's because these two domains are completely incompatible, that the source domain actually led the model towards like a worse direction than if it were just to start with the limited amount of information. So it very much is a balancing act. Selection of source domain is very important when dealing with it. And you need to be careful not to be completely like engulfed by the concept of transfer learning, that you just try to transfer even the most incompatible domains, because you could result in worse performance overall. Okay, so to conclude, we have our CNN layers. The more shallow they are, the more basic features that they hold. The deeper you go, the more complex information that you can, the more complex information that the deeper layer stores. Transfer learning leverages knowledge from other domains for when data in the target domain is limited. But the depth of knowledge transfer or the depth of fine-tuning matters and highly depends on the similarity of the source and target domains, as well as the size of the target dataset. So this is a hyperparameter that you'll have to tune to the methods that we saw earlier. Otherwise, you won't be able to get the full benefit from transfer learning. And so that's the discussion. Thank you very much for listening.
Thank you for the presentation, Christian. The floor is now open for possible questions that you might have on the presentation. If you want, you can send your questions in the chat, or maybe you can raise your hand and we will ask you to ask your questions personally. Anyone? Let's wait for a few minutes for questions that our listeners might have. Siguro, just to start off the questions, my main question, since you were able to explain the whole process of what transfer learning is all about, and also how it is being performed, some pitfalls and also some applications, can you like give probably a specific type of application wherein we can use transfer learning for medical imaging? Like in the examples that you have provided earlier, you have examples on yung pag-ride ng bike. I like that analogy. You have other examples as well in the presentation, but can you give like, can we do like a transfer learning for a specific, let's say, X-ray images, tapos you're going to use it for another medical application? Can we do that?
Yeah, so as long as your source domain and target domain are compatible with each other, so you don't have the risk of negative transfer, that is something that researchers have explored, transferring from one specific medical image modality to another. However, there has to be some similarity, as we know that, I mean, medical images, there are some large variances between different centers. So let's say one clinic can have a different structured X-ray compared to a different one. And so in that case, you could leverage transfer learning since your target and source domains are quite similar. However, if you just have a model completely trained on, let's say, one image modality, such as like fundus images, and you try to utilize that for something like X-rays, since your pre-trained model is highly specific, it's not general like the ImageNet data set, it may not have the breadth of features that that your target domain may be able to benefit from. So in that case, that could be an example of negative transfer where it would actually affect the performance of your target domain.
Okay, thank you for that answer. So basically, the presentation was able to cover everything about transfer learning. If I may, transfer learning is one of the older and more established studies or techniques that we use in computer vision. And I think not only in computer vision, but other machine learning tasks as well, wherein we try to leverage an existing set of weights so that we are not going to start from scratch. That's the main idea. And based on even papers from 2013, 2014, they have already used transfer learning so that they train on a very large data set. Then they utilize the learned knowledge from that bigger data set so that they can use it for other applications. So usually we pre-train or we transfer our learning from ImageNet, then we adapt it to other applications that we might have based on the target application that we are doing, no? And in this case, Christian is targeting medical applications, which is in line with your thesis, right? That's why he explained how transfer learning is being used in applications like this one. Okay. If you have no questions, can you please raise your hand so that we can move to the next presentation? Sige. So do not lower your hands. There's a question here. So if I use transfer learning that learn on ImageNet, I can use it for birds, planes, cars. What do you think, Christian?
Well, I think ImageNet already contains those classes.
Yeah.
Yeah, ImageNet is such a large data set. I think it has 1,000 classes, and I think there's different versions as well with more.
Yeah.
So it may already be capable of classifying birds, planes, cars, or other everyday objects. And so transfer learning may not be necessary because the pre-trained model is already capable of handling that classification task. But so the strength of transfer learning is when you have a different domain now from everyday objects. Let's move on to specific. And so we'll utilize the features gained from such a general task to try to limit the amount of training data that is used in our target domain because we already know certain basic features.
Okay, thank you for that question. Yeah, I agree with the answer. If I'm not mistaken, in the ImageNet dataset, there are a lot of classes of different types of dogs and different types of flowers. Kung hindi ako nagkakamali. I'm not too sure if there are planes, if there are cars in the dataset, but I would imagine there should be because we have like thousands of different classes in that dataset. Okay? I
Yeah, but
think
actually to add lang, if in the case that it doesn't have certain classes, so let's say you come up with like another everyday object which is not included in the classification or the labels of ImageNet, then I think it would actually be very beneficial because those two domains are highly aligned. You have the same sort of concepts as like shapes, patterns, etc. And so the knowledge can be very useful for if we're transferring that to a new class. Yeah.
right. Tama. Okay. Any more questions? Going once, going twice. Maybe you can still send your questions, then we'll acknowledge it later, but you can still send your questions in the chat. So, but for now, I thank Christian for the presentation about transfer learning. Thank you, Christian.
Thank you. Thank you.